Okay, we should be live, I think. I think it's live. Yeah, okay. I'm not dropping frames. Good. Okay. So today we'll be talking how you and I and probably the rest of the people in the world were created, or rather how we evolved into our current state. So, well, maybe not exactly how we evolved, or rather how evolution happens, because how exactly we evolved is a bit complicated to show, and show and calculate really. So we'll just use a much simpler model to show the evolution, let's say. And you probably stumbled upon the evolution videos on YouTube. There is a lot of them. They usually use some dots or blobs or other kind of creatures to show the evolution. There will be none of that. We'll just show numbers, but pure numbers are pretty bad to show, so we'll use graphs. And the best way to do this is Python. And the other reason is that I don't know how to show 3D in Python. But let's not be concerned about it. So the environment we'll be using is called Jupyter. It's basically a web interface for Python, and it's much cleaner looking than using PyCharm or any other IDE for Python, because you see the result immediately, not when you write the whole program. Rather, you see the errors immediately, because that will be mostly what we see. Like always, I don't know what I'm doing. Basically, I know a theory, I know a little bit of Python, but I don't have a clear path that will be exactly how I want to do. Basically, like always. Okay, so if you never use Jupyter, Jupyter basically uses notebooks to display its data, to calculate its data, and we want to create a new notebook. You can clicking the new button and choosing Python 3, because that's what I have installed. And for the nice graphs, we'll use the library matplotlib. I have no idea how it works, because I've used it for like 15 minutes before the stream, so it'll be funny. I would probably just look up a lot during the streams how I want to show the data I want to show. And the thing that I know is you have to write something like this. Because this makes everything happen for some reason. We also want to import the library, or more specifically the module from the library called pyplot. SPLT to not write the whole line. And we also want NumPy. NumPy is basically the god library for numbers. Not like a specific kind of number calculations, but more like general number calculations. NumPy as NP. Okay, to execute the line we use Shift Enter, and yeah, it went through good. So let's have a little bit of theoretical introduction to how our simulation Hello? For some reason the audio was not working. I just realized. I'm so sorry for that. What I was talking about. I don't know where it went when it stopped. Oh, I have some bad values. It shows me video input. Can someone tell me if the video is okay? Because I have no idea. Like it's I don't know. Because I think I'm not dropping frames. Yeah, I'm not dropping frames, but is it okay? Everything's okay? Can someone tell me? Okay. Okay. So back what I was talking about. First, there is our formula. So the population, the current cycle is the population in the previous cycle times the depth chance of each individual entity. Rather, we should say 1 minus the chance, because the depth chance will be how much died. So we not want to know how much is still living, plus the amount that will spawn each cycle. And we want the start population, and also we want to know the cycles, how many cycles we want to simulate. Let's say 1000, for example. Okay. Okay, this will be our start values, and now let's plot the numbers. So our x will be our days, so this will just be list of range of cycles, and then y will be calculated a bit differently, because we cannot just calculate like that, because I don't know if there is a formula for that for recurrent, but we'll just use a for loop. So for I in x, then to calculate the y. Oh wait, we also want the depth chance. Okay, let's do it like that. Just say that the chance will be 0.05, so 5%, and the spawn amount will be, for now it will be 1. And now our y, our new value, will be the previous value, so y minus 1, and at the beginning there will be start population times 1 minus depth chance plus spawn amount. Our basic formula, let it run. List has no, oh sorry, that's append. Too much JavaScript. Did I spell something wrong? Oh, I didn't execute this line. Okay, everything is okay. And let's now graph it. So that will be, I think, this. I hope. And it's not showing. Why it's not showing? Hello? Hello? Because there is the there are wrong numbers, because we have 1000 cycles and 1001 y, so we need to do x except the first, because the first day is already known. So it's like that. And now we have bars. Maybe let's do something else. Well, not bar, but maybe, I think it's plot. Oh, that looks better. But it's quite boring. Why it's boring? Because it's just a line. It's calculated depending on a formula. And it looks nice. I I won't argue that it doesn't look nice, but it's just a formula. We rather look at a simulation than a formula. So what can we change? Instead of just calculating death chance and multiplying it by previous population, we want to roll a dice for every person in the population and check if he died or not. So let's do that. So for entity in y minus 1, so the previous cycle, wait, because there's number, so we want to do range, and we can do it easier by just doing this. So it will be the new top will be 1 for x in range of y minus 1. If we need also a random number generator. Random. Okay, if random is greater than death chance. No, lesser than death chance. Sorry. And we want to get the length of that plus spawn amount. So we're getting a iterator for each of the we want to generate a pseudo list that has length of the previous population, and for each person, maybe not x, maybe let's do it like e. Oh, e is great, yeah. And for each one, we want to have a random chance if he will stay or not. If he stays, he will just add a 1 to the list. If not, he will add nothing. And then we get the length of it, so we actually have a simulation of it. And we just want to add new pop. Let's see how it will now behave. There is something wrong. It should be greater, equal, not. Yeah, and now our simulation is much more diverse, let's say, because sometimes entities die, sometimes they don't die, and there is a higher chance of not higher chance of surviving, but sometimes they die and sometimes they stay alive. And there are, for example, peaks like this when we have 27 entities, because there was a long chain of 0 deaths or 0 to 1 deaths, and then we fall to nearly 13 because a lot of them died at once. But we can see that it pretty much stays near 20. That's what we want, because from our formula it was 20. But let me drink. But that's a pretty boring simulation. Like, there's always 20 of them, and that's not how we actually live, because we don't just spawn. There is no chance of spawning like that. We usually are born. So and there is more births when there's more people. Like 2 people can only reproduce. Yeah, that's the word I wanted. Reproduce once per cycle, let's say, but 10 people can do it more often. More often? Whatever, let's not get into that. Basically, the reproduction rate, or the amount of births, is somehow connected to the number of entities we have. So let's add this feature. And if you think about it, it's basically like def chance. So we can add reproduce. So we can add that to our simulation just by doing basically the same plus the length of reproduce chance. I didn't specify it. Let's say like 0.02. It's a harsh environment. We don't want to reproduce. So, and now we want to add one if there is a chance. So there will be less. So if we got something between 0 and 0.02, we want to create another person. Right now it will be 1-to-1, so it will just clone itself, not actually reproduce. But let's not get into that right now. We'll talk about that later. And we want to add the length of it like previously. Oh, there is... I didn't... Yeah, now. And if we now check our what it's called, our graph shows the middle more in like what it is, 20, 32, 33, something like that. If we add more cycles, like 10,000, because that's still not that many, I think. Yeah, it calculates basically like that. We see that it basically leveled off about 35. We have some big peaks, like 55, wow. But we also have dips like 13. But the medium is about 35. If we run the numbers, it's basically the same that we would compute the difference between them and use that as the depth chance if it's greater than 0, and or as the reproduction chance if it's lesser than 0. So if previously we had a spawn amount of 1 and we divided by this, we would get 20. So the amount that our ideal example showed. And now, if you just not divide, subtract from the depth chance, we subtract the reproduction chance, we have 0.03. And if we divide 1 by 0.03, we get about 33. So the line that our graph shows. Not exactly, but moreover. More about. I mean this word. I don't remember the words in English. Okay, so that's good. Our graph still shows some good actual data that would be computed if we would just use a formula. And but that's a boring population. That's a stable population. That's good because we have a certain amount that will basically just hop around this value. So that's a stable population, but it's boring. It's basically one value. We want something more. Let's maybe check what happens if our reproduction chance is greater than our death chance. So let's run this. Oh, it's taking much longer. Let's wait. It's much longer. Why is that? The reason is that maybe stop it and run it for some less amount, like 100 to be enough. We see that now because our reproduction rate is greater than our death chance, our numbers skyrocketed. Like, let's see, in the 100th day we have already what, 550. If we go to 1000, I don't think that will be, I don't know how this will be, how fast will this be. Yeah, it's too long, because we maybe let's use a better method instead of this length. Let's just use like that. So count will be 0, and for e in range y dot minus 1, because that's a bit so slow to do the array thing. If it's lesser than death chance, then count minus 1, minus 1, this, and if it's done reproduction, this plus 1, like that. And the first starting thing will be spawn amount. Okay, and now new pop will be like that. Okay, and now it should run much faster. Huh? Oh, there is no this symbol. Still something wrong. Count new pop. It should be the new pop. And now it ran much faster, but it's something wrong again. If random is lesser than death chance, new pop minus 1. Yeah, that's correct. Thing. Hello? I don't exactly understand what's going on now. Y minus 1, so 10. At the start it's 10. We check if it should die. Plus y minus 1. We forgot about it. Yeah, right. It should be that. Oh, it's calculating still. Okay, let's let it calculate. So it's not much faster, but it's faster. I probably. Let's stop it. It's slower. Huh. That's interesting. It's interesting. I thought it would be faster. No, did I execute it? No, I didn't execute it. Okay, it's looking ahead for the 1000. Yeah. So we'll just why is it not showing? Hello? Oh, right now. So we'll just say at the 100 because that's also a calculation, because we randomize a number for each of them, and yeah, at the day 100 we have already 1000, because now it went much better, because each time we run it, it will be a different number, because that's how randomization works. So yeah, that's not a great population. Like, it's okay for the population. We have a lot of people or animals or whatever, but the problem is that that's not how it works, because there are constraints for the population, like food, shelter, wild animals, or any other thing that can happen to them. will affect how many of them actually can be. So let's right now let's not be concerned about how exactly it's calculated. Let's just add a some value that will limit them. It will be based on the population, because, for example, if we have a 100 of food, for example, the more people there are, the more will die of starvation. So let's simulate that. It's a bad vision, but it is what it is. And we'll not simulate for now the food or anything like that. We'll just we'll just add a variable that will just limit the amount in some simpler way. We'll call it crowding factor, and let's set it to something really small. And how the crowding factor will affect us? The crowding factor will basically increase our death chance as the population grows. So let's just add crowding. Let's execute this. Crowding factor times the previous population. Let's run the numbers. And now it looks much more different. And we can actually run it again. It's somehow leveling off, but not exactly. Let's run like 500, because now we can actually do it in reasonable time. And we see that it tries to level off, but it still has hiccups, like always. Like it will level off with hiccups. So it's at the beginning, it's actually increasing like crazy, like previously the exponential increase, but then it levels off basically. And the more we have people, there is like really steep curve down then. If we want to, we can actually do something like that, times 0.5 plus y minus 1, 0.5. Let's make it an end. And that'll be a little bit smoother to look at. Let's run it again. And we can basically see that there is a leveling off somewhere. Somewhere in the middle of like 40 and 50 basically. That's good. Our population is now again stable, but has the really nice growth at the beginning. And that will be a good representation of how actually things work. Because if there is more and more people in this world, it will be a little bit grim, but stay with me. Someday we'll run out of food, or rather our food production capabilities will be too low to suffice for that many people, and there will be a cap how many people in the world can be. Or if not, if we can invent some magical food that grows really fast and all, we'll still run out of space, or other things that are limited how many we can produce basically. So that's a good representation of how many single entities there are. But we talked about evolution, and right now we're only representing the amount of population we have. Right, by the way, if we use 0 as the starting amount, a new pop Why is that? Spawn amount. Why is that like 5 maybe? Oh, I think I didn't run the simulation. Oh no, why is that? Spawn amount, start population 0, then 1. Oh, that's why. So, if we not smooth it, actually, the smoothing should be done after, not the. Oh, the spawn amount actually blew thing away. I should run it in the 100 maybe. Oh, still no. Oh, it's ran. Okay, it's done. It's done. But why can't I show it? Hello? Hello? Oh, I stopped it, so that's why. And we have to run the first line again. The spawn amount just blows things. Oh, wow. Why is that? Wow, I didn't expect that. Huh, funny. Interesting. I didn't think about this. Okay, but let's not worry about this. We'll just use the starting population. No, something is wrong because am I not? What's going on? Because the crowding factor should. What? Why is it exponential? Why is it 10? Was it a million? What's going on there? Like, a second ago it was working, right? Why is it working now? Am I missing something? Oh, this. Okay. Yeah, now it's okay, and we can start with zero population now, right now. Okay, yeah. So it basically looks how it should. So nice growth at the beginning, and then a bit of stopping. We can simulate much more right now, and we'll show this. Yeah, nice beginning, and then leveling off. Okay. So we want to simulate evolution. So we don't right now. We don't want one. Basically one. Give me a second. I need to look at how to show. Okay, if I do this, it should. No, it shouldn't. I'm trying to show multiple lines right now. So matplotlib multiple plots. No, that's not what I mean. Okay, that's what I want. So basically like that. Okay, that will show two at a time. Okay, good. So we want to simulate multiple populations but in this in the same at the same time. So first, let's define a function that will simulate one cycle, and cycle, sim cycle maybe, and we'll take the previous cycle, previous population, so pref pop, and it will also take the characteristic of the entities. So right now we'll not worry about it because we have just one characteristic, so the growth, right? Oh no, we can do this. We can do this. So characteristics, and how it will work. Previous population will be an array of how many of different entities there are, because now we have different entities because there's mutations, right? Evolution is mutation, so something changed into something else. And characteristic will be an array of arrays, and the first array will be the different entities, and the second characteristics will actually be how the inner array will have three values. So the reproduction rate, the death chance, and the spawn amount. Yeah. So for each one, and the crowding factor will be the same for all. So that won't matter. So we can copy this for now. So for each of them, actually, so cur pop will be a new array, and for y and car in zip pre-pop characteristics. So we want to get the current previous population of this species and the characters of the species. We'll do this like that. So new population will be the car of 0. This will be the spawn amount plus y, because that's a previous population. And for each of them we want to check the car of 1 will be the death chance plus crowding factor, because crowding factor is universal, and it will be car of 2, so the birth rate. And we want to append y, we'll append current pop. And I think that's it. This other function will be, oh, there is something wrong. There should be in. No. Okay, so we can return that. And for each of our x's, we want to first we want to our y will be the, for example, we'll start with 10 of one and 5 of the other. And entity 1 will have spawn rate of 1, the spawn amount of 1, death rate of 0.05, and reproduction rate of 0.08, like our current one. And the E2 will have spawn amount of 1, death rate of 0.2, and reproduction rate of 0.1, for example. And now we can simulate, just do how can do this. y will need to be in like that. I'm going to return the current position. So return cur. I forgot about. Okay, and we want to y dot append sim cycle of what? Previous population characteristics and RF characteristics. So previous population will be y minus 1 like previously, and the characteristics are E1 and E2. And we want to plot the numbers. So we want to do pop1 and pop2 will be just zip of y, because zipping, like this is basically zip population 1 and population 2, and if a double zip is basically an unzip. Like double zipping is the same as what was double zipping with the zipping again, while deconstructing the array is basically unzipping. Complicated, you'll see how it works. And we want to show pop1 and pop2. So let's run this, and we have the two entities. And we can see that I think the second one is the second one is the pop2. So the one with the much higher reproduction but much lower death rate is doing much better than the other. But let's add something different. Let's add a mutation chance. So our new character will be a mutation chance, will be the fourth one, and it will have two things. First, to what we want to mutate. So in this example, it will mutate into the E2, E0 and E1 for the sake of good, and so it will mutate into the E1 with the chance of 0.01, for example. And mutation will only happen when we reproduce, not like always. And now we want to obviously change our function to include this reproduction rate. So our current population will basically be a 0 times ref pop, the length of this. Because at first, before the calculation, there is 0 of each entity, because there is nothing right now. And now we want to, instead of append, we want to just set it off. Let's do a integer right now and range length of cur pop. So we also want a index, and we just set it to the new population. And then let's check. Let's run the calculations for mutations. So for key and value in char3, first, if length of char is greater than 3, so it has the fourth value, the mutation one, we want to simulate the mutation. So for each possible mutation, our key will be to what it mutates, and our value will be to what chance. So if random.range is lesser than value, so there should be a mutation. Should be a mutation. instead increase the population of the entity that it mutated to, so +1 layer. And break the loop because it can only mutate once, obviously. And it's not exactly ideal because if you have a lot of mutation, the last one will have a lesser chance. But let's not worry about it, we'll change that in the future, in the near future. And obviously we can check if you want to check if mutated, so mutated equals false, because and we need to set it to true if the mutation happens, so mutated equals true, and if it didn't mutate, so if not mutated, we want to increase the origin population by 1. What's wrong? There is no this symbol, I don't remember what it's called. And now let's rerun our, it's not range, it's random, like that. Run our computations, and now we can see nothing different. Let's increase the chance. No, let's do it like that. So the E1 will have 0 as for now delete the mutation, and our E1 will have nothing to start. There will be none of them at the start. As you probably can see, they cannot be born, they cannot reproduce, they just won't exist if we don't start with them. But if we add the reproduction chance of, I don't know, 5% and run the numbers, as you can see, at the start nothing mutated, but then because they have much greater reproduction chance and much lower death rate, as soon as one of the blues mutated into the orange one, the orange ones blew up and dominated the orange. Let's make the reproduction chance, mutation chance lower, because I want to show something. Maybe it will, maybe even lower. And run it again, maybe even lower. Like I want to have it like super small. Wait, oh no. So maybe like that. So make it little really slow and add a lot of cycles. No, it's not showing what I want. What I wanted to show. I know why. Because we need a more prominent crowding factor, and now it will show, I think. Huh? Really? It's not showing what I want. Oh, I know why. I know why it wasn't doing what I want. Because our crowding factor right now is broken. We want to. The crowding factor should be calculated on the sum of the y, not on the because that right now crowding factor only looks at the population of the current entity, not all of the entities, not the sum populations. We want to look at the sum population. So the total population is equal to sum of pref pop, and we want to use the total population in the crowding factor, and now it will work much better. If we get it to work. Crowding factor should be... Why is it not working? Oh, I didn't update it. Okay. Yeah, that's what I wanted to show. A little bit lower cycles. As you can see, because now the crowding factor is actually working how we want. Why do I have two OBSs open? And I'm worried that I will close the wrong one, but so let's not worry about it. As you can see, now the population is actually, the crowding factor is actually working, because at the beginning, the blue graph is ramping up because there's no orange entities, so the blue ones can thrive. Obviously, there is some point where the crowding factor actually have a chance to do something and limit the maximum population, but that's good, the blue are thriving. And as soon as the oranges start to rise, the total population here actually is the same as here, but the blues have to move because the oranges want some place for them. We can show, I don't know how to describe it, like basically because of the crowding factor there is less blues because there is someone else beside blues. We can show that by plot x and mapping the y lambda x sum x y. So we basically sum each of the, calculate basically the total population of every stage. And maybe a list of that. Because it probably doesn't know how to show a map. Why is it not showing? Hello? PLT. Yeah. So the total amount here is really the same as here when they meet, but the blues has to go lower because the oranges want some place for them. Okay, so we have some evolution, but right now we have a really good example, really good scenario for the evolution, because the result of the evolution is better than the original entity. So let's add another entity, E2, that will have the same reproduction rate as the E0, but will be much more, the mortality will be much worse. And let's add the mutation. The mutation will be much greater than for E1. What? Oh, I didn't add the E2. Yeah. No? I will also need this. So it will be 0 for now. Too many values in the pack. I need pop 3. So we'll just do this for y for top in zip y just plt.plot. So we want the plot every, basically, like that. Pop, just pop. So not worry about how many of them are. The red one is the total population, the blue one is the original, the green one is the new one, and the orange is the orange. So as we can see, the green one sometimes sparks up. There are the peaks. There are the peaks for the new one, but it's really doing really bad. It's basically 0 all the time. The orange one is doing great, like always. But why? Why is the green one doing so bad? It has a higher reproduction rate. Higher reproduction rate than the death rate. So why is it dying? The problem is that the sheer amount of entities that live now, so the 100, is adding with the crowding factor. Right? Crowding factor times the amount of it is about 100, so the crowding factor is actually 0.1. So 0.1 plus the death chance is much greater than the reproduction rate. And even if we help it a little bit more, so let's add that the E1 will also mutate into the green one with 1% also, so a high percent. It will only spike up and still do really bad. Because the mortality rate is so close to the reproduction rate, and basically the can I scroll? Yeah, and the crowding factor is basically killing them all. But this is still a simplification. Really, it's okay a simplification because we actually have some mutation, but the mutations are really, really simplified. Instead of doing this multiple entities, like types of entities, we'll just do one starting entity, and every entity can mutate everything on its own. And let's see what will be the results of that. So instead of doing this, we'll just create a new function, simcycle v2, that will take the population and no characteristics, because every single entity in the population will be an array of characteristics. So and there'll be no mutation chance. Everything will have a mutation chance. So first, Alt Enter create line. Let's define a mutation chance equals to 0.01. No, 0.1%. I meant. And now let's delete this. And for each entity in previous population, we wanna try to reproduce if it wants to reproduce, if the chance is right, and try to mutate the new entity. It still will be like that. So it will be spawn, then a death, then reproduction. So let's copy this because I think it will be okay or not. We need a current population, so cur pop equals nothing right now, and for each of them, like that, okay. If the total population, I need to calculate total population, so it will be just, instead of sum, it will just be the length. We want to check if the E of 1 will be, sorry, there will be no spawn chance. There will be absolutely no spawn chance. So the first one will be the death rate. So if it wants to die, basically don't add it. Just continue. Because it died, it did nothing. Then, if it wants to reproduce, check this. This is wrong. For each of its stats, so the child will be the same as E, but for each of stat in child, we want to check if random.random is lesser than mutation chance. If so, we want to also create a mutation delta. So it will be just 1.01. Maybe no. Like the same for now. If so, we want to, maybe just 1%. So we want to do child. We want also an index. So zip child and the range of length of child. Child of E will be the stat plus random.random times mutation delta. And we want to add the child to the population. So cur pop append child. So if there is a child, we try to mutate every stat, and if it succeeds, we want to change a bit. So the current stat plus a bit, mutation delta times some random value, but some random value is between 0 and 1, and we actually want between -1 and 1. So let's see if there is a function for that. As I don't remember. There is random range, but it's not what I want. So we'll just do random times 2 minus 1. It basically scales it to from -1 to 1. And that's what we want. And if the child was great, obviously we want to add the population. And we want to return the current population. And now, let's do this. Oh, something is wrong. I forgot the sign. Okay. Then now we want to also graph it. But now the graph that we had before is pretty much useless. Because of the fact that the population is super, there's no types of population. So we could show the total population, but we have to show each stat in the different chart. And then we have only 2 stats, so I'll do a scatter chart if I find how to do this. Matplotlib scatter plot. Yeah, that's what I want. How to do it? Can someone tell me? No. Yes, this one. Okay, that's length space. So what? Yeah, I want this. Wait. Yes, I want this scatter. Okay, so nope. plt dot scatter. What? Oh, I understand. Okay. So we want to check for each of the what it's called, for each of the entities, how it's doing after some time. So we want to check the actual stats. First, we want to plt dot plot. It's plot, yeah. Plot the total population. So basically, the length of it at each stage. So let's do that. So it will be x will be just x, I think. Yeah, x will be just x. Let's do x, and y will be the total population for now. So at the start, we have for example, 2 entities with random. Oh, we need another function, I think. So this will be def create random entity, and it will return a random. So we'll just create 2 random values and put in an array. And we want a create random entity for x in range. What is called start population. Yeah, start population. Start population. Yeah, like that. So we create a number of random entities basically, and we want to plot the. I want to obviously run the cycles. So let's copy also the code in here. But we want to sim cycle the v2 basically, and there will be no of this. And we want to map it because we don't want to show entities actually, but we want to show the number of entities. So lambda x, and will be the length of x, and we'll map the y. Yeah, y. Oh, and this needs to be an array also in the array. Yeah, I think that's it. Let's see how it works. Create an entity. What's wrong? Start population is not defined. Start pop. It's called start pop. Okay. Current population is not defined. Where? Char pop. It's char pop. What's wrong now? Just as our input, so let's cast it as list. And it's not showing because something. Let's just do it again. And now it should show. Oh, I forgot to start the start population at 10. Now it should show. Oh, they died. Great. Let's generate them again and see. They died again. Something is wrong. Okay, let's see what's wrong because that's not good. Oh, I see. I forgot to add the. I basically was adding only the children. I didn't add the parent if it survived. So char pop append e, because we want to add the parent. And right now it's nice. We can submit it again and again. Oh, they died. And then, and as you can see, there is a lot of different values. Like it was 400, now it's about 450. It was 200. Why? Because there's different starting characteristics, and the mutation chance is really low. If we set the mutation chance to something really high, there can be two results. Basically, we see both results. So we skyrocketed because there was some really good gene. For example, 100 reproduction rate, or 1 reproduction rate and 0 death chance. That would be really good. But then the gene basically vanished because everyone mutated, because 0.1 is really high mutation chance. And there was not a lot of them, and again they rised, fallen, and again. If we set something like 1%, which is okay, we see the peak and the fall. And for example, there is a fall really fast. There will be a lot of different results that we can see. Okay, but we also wanted to do the stats that ended up winning, let's say. So, first, give me 5 minutes. I have to go to the toilet because I drank a lot. And I'll be back in like a minute or two. Let's mute the microphone to be sure. Okay, I'm back. And we wanted to show the stats. So, basically want to show the stat of the last generation, because that are the final one. We could show it the every generation, but it would be very messy, and I'm not really sure how to do it the best. I will try later, but right now let's show the last generation. So let's just get the last generation, and for each one place a dot. Wait. Last generation is Y. Okay. This is a list of entities. So if we do this, it's a list. It's two lists, one of X and Y. So this will be first what? First is what? Death. First is death and reproduction. Yeah, this. And we want to just plt dot what? scatter? Yeah, scatter. X, Y. Got 0. Something bad happened. Let me just print y of -1 because I don't know what's here. What happened? Hello, what happened? So, yeah. So, why? Oh, this is a zip object, sorry. Why? Let's do it in list. I don't know. There's a list of a lot of objects. Do I see? Yeah. So why is it something to do it in tuple? Tuple? Maybe. I've never done this. Okay, it works. I don't know why, but it didn't work previously. Something wrong again. Setting an array element of a sequence. We want to cast both of them to a list. So list, because they are tuples. I think that's what it is. What? Because they died or what? I think that's because they died. And something is wrong. How scatter works? Can someone tell me? Hello? I think that's how it works. Hello? Okay. So let's print that and print reproduction. So def is just a big tuple. Okay, that's good. I want that. Yeah. Why the plt.scatter isn't working? plt.scatter def reproduction. Hello? And I want lists of them. Okay, they died. Okay. Basically, everyone has the same stat. They have negative def and positive above 1. Why is everyone having the same stat? That's wrong. Wait. That's really wrong. Let's do 10 cycles. Because that's really wrong. Hello? Why is that? Am I doing something wrong? Let me see. Because everyone should be having a... Oh, there is another one. Oh, let's do... equals 0.1, I think. Oh, there are other. Okay, there are other. And can I show both of them? No. Give me a second. Plot lib 2 different two plots. How to do 2 plots? What? Okay. Okay, I don't. Okay, what? So it should be like this. PLT.subplots, and I want n rows equals 1 and calls equals 2, and now axis of 0 is scatter. Oh, axis to 0 is the plot. So it's this. And axis that 1 is this. I think. Let's see. Yay! Okay, it looks okay, I think. So there's one here, but let's set the mutation chance to really low, I think, maybe. But there's only 2. Why is there only 2? Yeah, whatever. Whatever. So these are the... Maybe if I add a bigger mutation chance? Oh yeah, we have a really low mutation chance. We want a really big mutation chance. No, that's not what I want. Why is that? Interesting, because the result should be like a lot of dots. A lot of dots. But it's not. Okay, let's do 1 cycle, multiplication to 100. If that's not it, yeah, that's what should happen. And okay, there shouldn't be split like that. Let's see if what works with 2 cycles. Okay, they're grouping, but it should group, but not like 3 points basically. Yeah, because they are basically the same point, and that's not good. What if we do this? A lot of them died. Okay, that's okay. And now let's do the lot of cycles. That's really strange. And there's all... Oh, why is that? Okay, they are perfect at surviving and they are perfect at reproduction. They're really stable. I don't want that. I don't care. I don't care. I don't care. Yes. So they're basically evolving into the perfect entity that doesn't die and doesn't... it has the so low death rate that it offsets the... Why is that? Why they are all evolving into 1 point? That's not what I wanted. Let me see. If... Yeah... Oh, I think that's the problem. Okay, I need to do this. X in... for X in E. Yeah, now it's working. It's because it was copying by reference. So now it's working. And as you can see, it's funny how it basically jumps and there is a lot of turbulence. And as you can see, if I had a like reasonable mutation chance, so 0.01, they are basically grouping in a couple of spots. And the more mutation we add, there will be more spots that they are grouping in. I still don't like that there is a lot of this. Yeah, but it's right. It's right because it's probably because the reproduction rate is much higher than the death chance. Yeah, the def chance is basically hovering over 0. But how long are we streaming? It's near the 1.5 hour mark, and I think that will be it for today. We'll probably continue tomorrow because I have a lot of time now. Probably about 7 p.m. UTC or whatever it's called. There's plus 0 time, whatever it's called. I don't remember. And we'll continue from there. But we today can quickly add one more thing. Because we want to make this a little bit more realistic. The death chance is basically bullshit. Because there is no, like, we as a species cannot just do, I will just make myself less diable, not diable, less, lower the death chance of myself. That's not possible. So, instead of death chance, let's add age. So, our entity now will be composed of something else. We'll have the traits, and will be the thing that we can mutate, and there will be age. That will be 0 at first. So we want for each child, we want to do for each entity, we want to add the age every cycle. I think that's how it's done. I don't remember. Don't quote me on that. And we want to mutate, obviously. Copy it. That's how I will copy an object, by the way. Dictionary, but whatever. It's an object. Too much JavaScript. And we want to child.traits, and length of child.traits, and child.traits, like that. Yeah. And we want to set the the child, like that. Create a random entity. We want to also create create entity, and create random entity will just the create entity will get the traits, and the traits now will be x for x in traits, and the age will be 0, like that. And create random entity will now return create entity with traits for random and random. Yeah, like that. And basically our the entities will work like that, such as the def chance will grow, will make a global def chance. It will stay really low for now, and instead of having a trait for that, we'll have a the def chance times the e.h. So the older it is, there will be a higher percent that will die. Let's see if it works. Okay, so I cannot do it like that. I have to do this. That's okay. Traits Oh, and you can just do create entity with traits, like that. I think that should be it. No, dict has no attribute age. Oh, here. Age. No aid. Age. What's wrong? Here 0. Super. Okay, that's nice. Oh, because traits like that. It computes. Oh, and we shown age. We don't want to show age. We want to show the traits, but that's something. But I don't like it. Why is that? Obviously this chart is wrong because the age. No, we can do the age actually. I see. So we need to map. Yeah, that is correct. But the last one, we want to map. So the last one, want to map lambda x, and x is the entity. So you want to map into x traits age. Traits dot 0, and the other one will be x age, like that. And we want to map this. Yeah. Valid syntax. What? Oh, we forgot this. Expected to tuple, because wait. It's basically yeah. So I want to unzip it. So we want to do this and zip. Too many. Yeah. So this is age. So we have a lot of really young ones and not a lot of old ones. And you see, basically, they want reproduction rate, like they want to reproduce always. We will make them reproduce less in the next, on the next stream. But for now, that's it. We made our first shown how we can limit the population. Then we shown how the mutations work with just set types of entities, and finally we shown a little bit more accurate example of this when every trait can mutate. In the future we'll do something much on the next stream, probably tomorrow, we'll do something much more advanced. So we'll probably do like speed, food, and all of that. But that will be for the future. Right now, that's it. Thank you for watching. Obviously, it will be on YouTube. And yeah, that's it. Thank you.